Hello, this is Rick Riss. I'm a senior consultant at ARC, and today we will be talking with Albert Rooyakkers. Albert is the founder and CEO of Bedrock Automation. Welcome to this podcast. Albert, I'd like to start by asking you, why does industry need OSA? Open Secure Automation.
Good to be here, Rick. Thank you very much. There are two important pieces to that question. It's the open and secure, and which are a bit of a dichotomy, but let's explain. Traditionally, automation users are sort of forced in this proprietary incompatibility solution, in that from the sensor up to the enterprise, it was a single vendor that provided everything. And this worked for a very long time, but it limited the amount of innovation and the ability for technology to accelerate in any one of these given technologies. So an open system means that with a limited number of well-defined interfaces, a user should be able to pick and choose the best technologies. And this will allow the best cost at the best functionality for the given application and the given customer. Let me give you a key example. For us, would be one of our customers. It's a government building automation project, which has WAGO, low cost, distributed discrete I/O, connected via gateways to our backplane with redundant control, and connected by a network to inductive automation SCADA, all protected by Allen Bradley UPS. Now, perhaps traditionally a vendor would not like to, have it that way, but I think that that's kind of cool, because that allowed that particular user to take the advantages of the technologies and the price in each one of these segments and put it together in a building block approach and get a best-in-class solution for their application. So that's the example, where it rings true. Now, of course, the key thing is security, and security matters across the board in automation in an enterprise. But in an open system, it's even more so important, because you're going to require, again, these clearly defined interfaces to have certain technologies and standards applied to them, so that the data transfer and the computation and communication that exists across these interfaces remains cryptographically secure, and authentication exists as well.
Thank you for that, Albert. It was a good description of open secure automation. A lot of other suppliers bolt on their security. How is your Bedrock automation platform different?
Well, we talked about it in the phrase of bolted on versus built in, or built in versus bolted on. And we use an analogy that's biological, and give an example of a virus, which unfortunately is an analogy that's tragically relatable to everyone today. But if a system is built in, has built-in defense, just like your body, then your defense exists at the smallest common denominator, which is at a cellular level, and your body is vaccinated. So if you have bolt-on defense against COVID-19, you're wearing masks and suits and gloves, or if you've developed immunity or a vaccine is created, then you get rid of the mask and the suit and the gloves, and you can coexist with the virus because your defense has now been built in. Well, the same thing happens with digital systems. In order to really solve the problem, you have to start at the smallest common denominator, which is the transistor, and you build from there. So you need specialized transistor computation technologies that ensure that the system will have a secure boot, meaning that the code, the firmware, the boot ROM, the application is intrinsically secured into the component itself. And the attack vectors at the submicron and at the component level are protected. So then you start building from there with secure RTOS, with anti-tamper technologies, and various other components and pieces that ensure that the system will be intrinsically secure. Now, these are fairly advanced technologies that were used just recently in the high-end aerospace and military systems. And it's now really commercially available for the company that wants to start with a fresh sheet of paper and design a system from scratch, incorporating these kinds of technologies. And then over top of all of that, you need to address the supply chain. And the supply chain is an extremely difficult problem to solve because we are in a global supply chain model. So everywhere the components and the boards and the firmware and the software and the applications are created, you need a chain of trust, and you need to ensure that the attack vectors for malware do not exist across the entire the entire supply chain. So it's a pretty complicated problem to solve. And so either the vendors decide they're going to solve that and bear the technological, crunch and the cost and the burden to make it work from the beginning, or the user has to bear that cost over the life cycle of the technology by continuing to try to maintain a bolted-on defense. It's really one or the other, and that's the big difference. Does that make sense?
Yeah, that does make sense. In fact, it was a very good analogy. Basically, you've built in antigens to your system, and you're virus-free. Mm-hmm. So you're immune to some of the viruses, essentially, but also, I assume, in the communication side. Okay, so the next question is that when you have to communicate with other systems, you often are using OPC UA. It seems like it's very widespread. Can you explain how you keep OPC communications to third parties and enterprise systems secure?
Yeah, that's a very good question. But that involves a lot more thought and care. OPC UA as a standard has come a long way in defining security approaches to security. What's important, first of all, is that the client and the server is usually in the end equipment, the OT equipment, and the client is in the enterprise side. But both sides have to ensure that they that they support TLS. So with TLS, you can create a tunnel, a secure tunnel, and you're off to a good start. Now, the problem or some of the deficiencies with OPC UA is that OPC UA specifies that certificates need the IP address and the name of the device. Now, this makes sense in the context of self-signed certificates. And for some users and some applications, this is okay. But in many, enterprise and industrial applications, it really is not. And you need to have a third-party certificate authority provide the certificates. And that becomes really difficult because in that case, you need both the IP address and the name of the device. And this is very, very hard to do in the runtime world. And it also makes replacing a device and maintaining the devices rather complicated. So there's some really good progress that's being made, and you will certainly have an intrinsic level of security if both the end device and the IT enterprise devices will logically connect and support TLS. Then ensuring that the keys and the certificates are properly managed, you're off in the races. So there's room for improvement, and there's continuous improvement in that area, but it's come a long way.
One of the other key problems, of course, with any control system is how you go about programming it. The IEC 61131 standard with the IEC 611-499 extension standard defines how PLC programming describes function blocks, ladder logic, and structured text. How does the Bedrock automation comply with these specifications, make it easy to implement complex control systems?
Yeah. So probably the most important thing that's happened to the automation industry is what's happened in software and the long-term evolution and now truly widespread adoption of 61131. Now, there's really two primary paradigms for implementing control. It's blocks and programming languages. And 61131 implements the language paradigm, even though it includes function block diagrams and the ability to create block libraries. Foundation Fieldbus, not to bring that in, but just for a moment to talk about that. In contrast, Fieldbus offered really the only fully standardized block set. Now, 61499 originates in an intellectual exercise from academia, and the data hiding is a basic principle of 61499. So a block has a defined interface, but you can't see inside of it. So there's also a basic concept that new blocks can be composed out of existing blocks to encapsulate more complex functions. So anyway, I don't want to spend a lot of time explaining that, but the importance is that, there's two different strengths and fundamental capabilities in these two standards. Now, we adopted as our runtime programming environment, CodeAssist, which is out of 3S in Germany, one of the leading, if not the leading set of tools for 61131. And we are certainly keeping an eye on 61499. And I think that 61499, while it incorporates some really cool ideas and will allow you to more rapidly create or replicate the kind of elegance that you had in advanced control strategies in the DCS world, we don't see wide use and wide adoption. It's not to say that it won't happen. These things will take time. So we are dabbling in it. We're keeping familiar with it. We see many different ways to deploy it in any kind of a third-party open set of tools. And, the user community has to train itself and evolve with it. And, all of that will merge in the most effective way. So all of our tools are based on 61131, based on a de facto tool in the marketplace. And we're keeping a close eye on 61499. Now, the users have made huge strides in building libraries and by, sourcing open source libraries like OSCAT and PLC Open and others. So that's evolving as well. And you'll see more and more the users will have the ability to, cut and paste and copy and download, functional elements in the 61131 tools and 61131 library and 61131 blocks. And we're seeing customers seeing tremendous efficiencies in this approach. So it's embedded in the design, it's embedded in the principle of Bedrock's platform, and it's probably one of the most important pieces of our differentiation puzzle. Does that make sense?
Let me that brings up a question for me, Albert. Obviously, the Bedrock platform must come with a sufficient library of highly capable function blocks, PID, timers, sequential functions, all of these things. But also that means it implies that system integrators and implementers can build their own libraries and their own function blocks and therefore enhance the overall capability of your system.
That's true. Absolutely. We see that across the board. Sure. Everyone's, doing their own thing. And very quickly, with a limited amount of training, any experienced process engineer or automation engineer will start to have their own ideas. And we've seen some very, very cool things from the system integrators and from the end users. Absolutely. And the people get very excited about it.
Great, but your basic platform still has a fairly capable set of function blocks. So in many cases, all they have to do is pick functions out of your function block library, connect them together, and they have a working control system.
Yes and no. We're not far enough along in that. We have built a few of the primary functions. We don't really want to get too far down that path because everyone's going to have a slightly better idea. And the user community is really developing it much faster than we can. So we don't want to get stuck in that trap. There's certain absolute fundamental elements, like for instance, we have a really cool killer PID block, which is absolutely important. But, you build something and someone wants to do it their own way. So that's the trade-off.
So Albert, thanks for the explanation on the function blocks and the capability of programming your system. We both know that it takes process experts to implement control systems and build the user interface. What are the key partnerships that Bedrock uses to build these control systems all around the world and in different industries?
Again, across industries and across geographies, there are literally thousands and tens of thousands of system integrators. These are often regional companies, sometimes just a dozen people, sometimes with large multinational footprint, perhaps like Wood Engineering or others. And they do that for a living. They deliver solutions, but they don't have a control system. So it's an ideal partnership for us. And we sign on, and we have a formalized process for training and certification of the system integrators. And together we bring solutions to the customer. And so it's really quite elegant, and it scales. It's the ideal way for cost reduction and cost optimization for the user, because it's kind of an on-demand or an Uberization of the full turnkey solution. So we have many integrators. I don't know how many dozens of them, mostly in North America, some in the Middle East and Europe and Australia and a few places. And we will expand on these system integrators as our market demands and our customer demand. It's a win-win for the customer, in particular for the user.
And you have also tend to have partnerships with other software suppliers. I know that you're often using inductive automation, but you're not necessarily tied to any particular graphical user interface. Is that correct?
That's absolutely correct, and that's an extremely important point. I go back to my story about this large building automation project. It was the customer that chose inductive automation. So by having a clearly defined interface, in this case it's OPC UA, the interconnection between SCADA as a tool set, as an environment, and the control system is almost plug and play. For the first time, there's often a little bit of confirmation and stress testing and other things to make the connection work, but it's just a small fraction of the complexity that would typically exist in the past in order to get various paradigms of software to interconnect and operate. And so there's a prime example. Another really big example for us recently was when we partnered with FlowCal, and FlowCal is sort of the gold standard for API fluid measurement and custody transfer. And so by partnering with them and bringing the best-in-class software for measurement and custody transfer, we incorporated that into our control platforms, into the backplane and RTU style controllers. And now you have a fully functioning, state-of-the-art, cyber-secure flow computer. So that, as in one fell swoop, integrates PLC functionality, DCS functionality, electronic flow meter functionality, really all in one single platform. So that's our direction. You'll see much more of that in that, Bedrock is a set of platforms, and it's really a software-centric roadmap. And we will partner with the best-in-class companies that are providing analytics, simpler footprints of AI, and industry-specific or machine-specific applications that will run on this high-performance secure platform that's our Bedrock OSA. So we're proving that this idea is real, and we're bringing it to the market.
So Bedrock has quite a suite of I/O modules and I/O capability to communicate with all kinds of field devices, and also the controller, fault-tolerant controllers for executing control algorithms. And apparently those control algorithms are pretty good for things like flow meter calculations. Is there other plans in the future to expand beyond the controller to give a more general purpose computing environment or an HMI? How do you see Bedrock automation expanding? Yeah.
We've put so much horsepower by using modern electronics and modern digital semiconductor designs that it's orders of magnitude of what's typical of a more modern PLC or DCS platform. So already people are running things on a controller that you normally wouldn't run. An example would be cyber analytics. And so today you have companies that sell hardware, software services to do behavioral analytics, intrusion detection, and these kinds of functions that give you some eyes on the cyber world down at the edge of your process. So we wrote that code and built that functionality, and we poured it right into every single controller. So it's running as part of Secure Boot, and it's a pretty advanced analytical cyber analytics package, and it's built in and it's free. So that's an example that you simply wouldn't have the horsepower typically to do those kinds of things. We even have an IO module that will run PID and full regulatory control right in an IO module. So the idea of running your control strategy in the IO, in the controller, in a server, wherever you want that to exist, we've already been demonstrating that. You'll see in the near term, we will continually improve our hardware platform. And there's really only one piece missing in having a very, holistic solution. And that is, to what degree do you bring edge computing into the OT environment? And how much horsepower and how big of a footprint is that application? Does it make sense from a memory computation, architectural perspective, and security perspective? Does it make sense to put it right in the controller, in the IO module, in a temperature or pressure transmitter, or in a VFD, or in some other, edge computation device that's out there as a ruggedized computer? So this is stuff we know how to do really, really well. And you'll see us, constantly pushing the envelope. And what you get is this extremely flat and extremely advanced architecture.
So, Albert, Bedrock Automation can implement firmware upgrades throughout the life cycle of their product. How do you do that without taking the process down?
Very, very good question. And firmware upgrades, software maintenance, is perhaps the most expensive life cycle cost element. The way you do that is through redundancy. And properly engineered, properly designed, properly deployed, a redundant system will be able to upgrade itself or by instructions from the user without interrupting the process at all, without missing a single control cycle. And we are already demonstrating and shipping that functionality in the system today. And it took a long time to engineer that and design that and make it work flawlessly. So imagine customers, users on upstream, midstream, or any infrastructure that has highly distributed or large numbers of controllers within a facility or across a process infrastructure. Imagine being able to upgrade it as easily as you would upgrade your iPhone, and you press a button and that system will do an automatic sequential upgrade of one of the redundant pair and do a full firmware upgrade, full reboot, and full diagnostics check, and then compare itself to the other processor to ensure that the databases are identical. And then that controller or that device, an IO device or any module in the system, then takes over. And the second device does the same process. And when it's done, it does again authentication, validation, database check, and they remarry as a fault-tolerant pair or a redundant pair. And that all happens without the person, touching it. And it happens literally within minutes. Within a couple of minutes, you can upgrade an entire control database. And through the encryption, authentication, security, role-based access, all the technologies are built into the system. That means you can do that from anywhere. An engineer or person that's predefined biometrically and authorized to do that, that person could be standing in front of that device, in front of that system, or could be anywhere in the world over a public or private network and execute the same task. So that is a very, very important, very cool thing that you can do with a modern system design, and that's what we've built into the Bedrock platform.
Thank you, Albert. I think we'll probably bring it to a close here.
Okay.
ARC would like to thank Bedrock Automation for giving us this insightful update on automation security.